cyclotrons and magnetic fields. In this video, we'll be covering the role of the magnetic field in the cyclotron, looking at the period of a particle in a cyclotron, and finding the energy of a particle that is emitted from a cyclotron based on its radius. I recommend watching this video with the other one of this series, which investigated the role of electric fields. I've provided a link at the end. So cyclotrons are often used to accelerate particles to very high speeds to create isotopes. And these isotopes are typically used in medical purposes. Passing a charged particle between the Ds can increase its speed and kinetic energy enough to be able to perform what we want it to. Now these energies can be so high that it's impractical to do this in one linear shot. So particles in a cyclotron actually go through a much lower voltage, but multiple times. And this repeated occurrence increases the speed of the particle each time to get the final speed that we're interested in. So this graph just looks at a particle over the course of its journey through a cyclotron and its velocity. When the particle is within the Ds, like on the left situation here, it does not accelerate. There is no electric field inside a hollow conductor. So in this area, the magnetic field allows it to turn, but the particle itself does not increase its speed. Between the Ds, however, there is an electric field, and every time the particle passes through this, it increases its speed slightly. And you can see this stepping motion that happens. So every time it is between the Ds, it steps up a little bit, and over the course of multiple rotations, you can see its velocity increasing every single time. The final result you can see at the end here is a great increase in speed, but to do this in one shot will require a lot of voltage, and that can be expensive and dangerous. On the screen on the right here, we've got an example of a particle that's within the Ds in a cyclotron. The magnetic field in this example is denoted by this pink box. I'm just going to delete it just so it's easier to read. When the particle is in this area, it's subject to the magnetic field only. It travels at right angles to the field, as the magnetic force using the right hand rule is perpendicular to the direction of travel. This results in that circular path, and when the particle is passing between the Ds, so just in this thin zone that travels down here between the Ds, its velocity increases every time. And from a previous lesson, we derived the equation that the radius of motion is based on the particle's mass and speed, but also the charge on the particle and the strength of the magnetic field. If the particle increases its speed every time it is between the Ds, that's this velocity term getting larger, the radius gets larger on each pass. This results in that spiral path. In order for the particle to accelerate when it's between the Ds, the electric field has to be going in the right direction. So on this diagram here, if the particle was passing in this location, we want it to increase its speed to the left. But then when it comes down to this location, we want it to increase its speed to the right. So that means the electric field has to switch. And we can find the change in frequency of this electric field if we can find the period of motion of the particle. Now, although the particles are only increasing their speed between the Ds, they are changing direction due to the magnetic field the entire time. The magnetic field in a cyclotron covers the entire cyclotron, so you can see that it's clearly turning in this direction, but it's also turning between the Ds. Again, we find the direction of this using our right hand rule. Alright, let's start by looking how far the particle travelled. So because it is a circle, the circumference of a circle is 2 pi r. And the time that it takes to travel this distance is distance divided by the velocity. Therefore, the time for one rotation is 2 pi r on v. And this you can find on your formula sheet. We also know that the radius of travel is given by this equation here, derived earlier. Therefore, we can rearrange this in terms of v and substitute that velocity back into this equation, and simplifying will result in this final equation down here. Now, what we can see from this equation is that the time for one revolution is independent of its velocity. And from this we can calculate the fixed rate at which the current must be alternating between the Ds. So frequency is 1 over the period, and so we just flip the fraction and we find that the frequency of the alternating current is given by this equation. And what this means is that the alternating current depends on the charge of the particle, the strength of the magnetic field, and the mass of the particle. The second equation that we're going to derive is looking at the energy of the particle when it leaves the cyclotron. For a single pass between the Ds, the particle gains the energy equal to Q delta V. And the energy increases every time it passes as the speed is getting faster and faster. But to find the total speed, we can look at our kinetic energy formula, which is half mv squared. Now, if we know the mass of the particle, and rearranging this equation here for V, substitute it back in there, we find that the energy of the particle when it leaves the cyclotron is given by this equation. And you can see here, the energy of the particle is dependent on the charge of the particle, the magnetic field, its mass, and also the radius of the cyclotron. Having a look at the diagram on this page, identify the location where particles accelerate. Additionally, identify the location where particles increase their speed, and is this different to part A?